Hello. I don't know if this is working or not. I think it is, so we're gonna roll. Hey guys, so I have posted these notes to Google Classroom, so you can have them in front of you too. But I think when you're just looking at a note sheet and then you're looking at a PowerPoint and you're just copying over, I don't know how much of that actually sticks up here. So we're going to try to treat today like it's a day in the classroom. Okay, so I'm going to go through this. We're going to talk through it. Hopefully it works. I don't know if it will or not. I don't know. I'm just going to try and see if I can write on this. I can't. See, I can't even write on the screen. So I don't know. We'll just try it and we'll kind of figure it out as we go, right? This is new for everyone. So let's roll. So I'm going to go through, I'm going to talk about solutions and salvation. Not salvation. That's different, right? Salvation, that's different than salvation. And so we'll talk about what that is. But we're going to talk through these. While I'm doing that, fill out that note sheet, okay? So your homework today is just when you're done with that note sheet, go on Google Classroom, click the turn it in button. Done. That's all you got to do, okay? Fill it in, turn it in, done. Now, there is, obviously you're watching it, there's the V.O.D, the God, and the quad, right? Video of the day, gratitude of the day, question of the day. So you got to do that too, but that doesn't take very long. You already started that, okay? But the homework today, turn in your notes. Done. So let's roll. So real quick, let's start with some definitions. Solution. It's a group of molecules mixed in a completely even distribution. Okay? So you have molecules and you have them mixed. Another name for evenly mixed distribution is something called homogeneous or homogeneous mixtures. Okay, homogeneous or homogeneous. Homo is a prefix that means the same. So everything is mixed. So I got three pictures on my screen. I have some chicken noodle soup, I got some soda with some ice cubes in it, and then I got milk. All right, and the question on the screen says, are these homogeneous? Well, I don't know. What's homogeneous? Remember, homogeneous means it's evenly distributed so that everything looks the same. So when you look at the chicken noodle soup, you got chunks, you got carrots, you got celery, you got chicken, you got broth, you have all these things. And yes, they're mixed up, but it's not even, right? It's like, well, it looks like there's more celery on the left than there's on the right. And I can definitely see where the carrots are versus where the chicken is. It's not even. So that's not a homogeneous mixture. It's a mixture, but it's not homogeneous or homogeneous. How about the one in the middle? Is that homogeneous? Is that evenly mixed? Well, I would say the soda is evenly mixed, but we have big chunks in there, right? We call them ice cubes. So I can see where the ice cubes are and I can see where the soda pop is. And, yeah, they're mixed, but they're not even because I can see the different parts. But now throw your eyeballs over at the milk, right? Milk is made of different things. If you ever let it sit out or if it ever spoils and gets rotten, or you'll notice that milk will eventually curdle, right? That's where we actually get cheese from. That's where we get yogurt from, is curdled milk. It separates into different parts and it gets solid. But when it's good, when it's fresh, when it's what we think of as milk, all those different parts that are in there, the cream, the fats, the proteins, the waters, they're evenly mixed. And you can't look at milk and say, ooh, look at the protein. Ooh, look at the fat. Ooh, look at the, it's just milk, right? It's a evenly distributed mixture. And we call that a solution. A homogeneous mixture is a solution, okay? Now, two other words I want to get to you quick, solute and solvent. So today's going to be heavy on the vocab, and we'll do some more vocab tomorrow with you. Try to nail that down because that's important, right? Solute and solvent, they start out the same, S-O-L, S-O-L. The difference is the suffix, the ending, right? Ut versus vent. Solute is the thing that gets pulled apart to mix in the other liquid. In other words, it's a thing that gets dissolved. Now, I called it pulled apart, but it's a thing that gets dissolved. Solute gets dissolved. Solvent is the substance that actually pulls the thing apart, and it's usually a liquid. It does the dissolving. Solvent, solving, does the dissolving. Okay, so solute, if you look at the bottom, I have what looks like a blue crystal. Okay, that's cuprous, it's copper nitrate. That's that blue crystal there. The solvent is water. When I mix them together, I get blue water, right? The crystal dissolves in the water. The solute dissolves in the solvent. Now, when I dissolve the solute into the solvent, I create a mixture called a solution. So going back a slide, right? A solution is when the groups of molecules are mixed and evenly distributed. Okay, and that's a solute and a solvent. Now, yesterday we did a little phenomenon looking at M&Ms dissolving. So again, you could get extra credit here. If you didn't do that yet, go ahead. Try this at home, take a pic and send it to me. They kind of did a random, or I mean, I guess it's not random. It's what? Orange, brown, green, red, orange, blue. So I guess maybe it is random, but they spread out their colors and try a different pattern. Try different lines or shapes. Don't do a circle. Do a zigzag, or I don't know. Go ahead and try it. But then in yesterday's assignment, I said, explain what's happening. And then I said, explain what's happening using solvent and solute. So if you did that, going back again, solute, solvent. The solvent is the thing that does the dissolving. So in our phenomenon yesterday, the solvent was the water. It dissolved the colors. The solute is the thing that gets pulled apart. In this case, it would have been the M&M. So a great explanation for this is that the water dissolved the M&Ms. That was one word, dissolved. The solvent was the water which did the dissolving. The solute was the M&Ms that got pulled apart and dissolved. Okay, so those are new terms, but you got to see them in action yesterday. Now, there are some ways to maybe help you understand it a little bit better. There's two other words I want to give you. They're really just adjectives to describe solids. One is soluble and the other was insoluble. So if something is soluble, you can dissolve it, right? You guys know that if you take salt and dump it in water, it gets dissolved. We call it salt water, right? And it just looks like water till you taste it and it's like, right? Whoa, that's salty. It gets dissolved, salty like me. Yeah, you're thinking it. I just said it, right? Okay, it gets dissolved. It's soluble. Other things are not dissolvable. So in the picture there, I have some sand. You dump sand in water, they'll mix, but it doesn't dissolve. It's not dissolvable. We call the sand insoluble. In meaning not. We call the salt soluble. All right. So hopefully you're filling out your sheet again as we go. We're almost done. Stay with me. You're doing great. What happens if I take two liquids and move them and mix them together? Okay. Sometimes if you, for example, if you look at vinegar, I don't know if you guys have much vinegar. We use it in foods. It flavors foods for us. I shouldn't say this out loud, but old people especially love to use vinegar to clean. It actually is an acid, so it's a cleaning agent. I know my grandma always cleaned with vinegar. She'd go in her house and be like, "Oh, what is that smell?" It was clean, but it'd be a little stinky. So vinegar is actually made of acetic acid and water, and you mix those together, it makes vinegar. So if I take vinegar and I take water and I mix them together, they'll actually mix. They'll dissolve into each other. We call that miscible. Sometimes liquids are not soluble. They're insoluble. They will not dissolve together. And water in oils is a great example of that. If you ever had a lava lamp, those I always thought were kind of fun. To play with and to watch, and you could kind of just stare off watching the lava lamp. That's just water and it's an oil. They don't mix and it makes these bubbles and they don't blend together. If two liquids don't mix together, they don't dissolve together, it's called immiscible. Okay, so miscible, liquids dissolve together. Immiscible, liquids that don't dissolve together. So it's really the same as our previous two words, soluble and insoluble. but it talks specifically to liquids. Okay? So the last component I want you to get is this solvation. Solvation is the process of surrounding solute particles with the solvent. Now let's reword that, breaking down solute and solvent again, right? The process of surrounding solute. Now remember, solute is what gets broken apart. It's the M&Ms. It's the salt. It's those blue crystals, okay? Gets surrounded with particles of the solvent. Solvent is the thing that breaks up the solute. It's the water. It's alcohol. It could be any kind of, it could be an oil. It could be any, usually a liquid again, that does the dissolving. Now the universal solvent on our planet is water. It dissolves most things, not everything, but most things. That's why when you get your hands dirty, you go right to the sink, turn on the water, right? And most things come off. If not, you add some soap, and also it'll come off because soap helps with that dissolving process too. Okay, but solvation, what happens is the dissolver, usually water, surrounds the particles of the thing that gets dissolved, and that's called solvation. And we'll talk more about that tomorrow. So what causes this solvation? Okay. Now, not all substances are miscible, remember, or can be dissolved into each other. What determines whether they can get dissolved or not is their chemical composition. You got to look at the molecules themselves. There's this thing called IMFs, intermolecular forces. We'll talk about that in another unit. We're not there yet. But IMFs cause things to be attracted. And really what it determines to is what's called the polarity. Now, we talked about that a long time ago, right? That was probably try one. But a polar molecule has a positive end and a negative end. A nonpolar molecule, no charge. And so what happens is polar things like polar things. Charged things like charged things. Non-charged, non-polar, like non-charged things. And so polar dissolve in polar, non-polar dissolve in non-polar. Okay? It's why if you get oil from a car in your hands and you go to the sink and you try to wash it off, it's like, ugh, it doesn't work. You got to use something else. You got to use some kind of solvent. Okay? You got to use like mineral spirits. You got to use turpentine. You got to use lava hand cream, something that is actually a non-polar like oil that will dissolve and break up that solute. Okay? And we'll talk more about this, but that's solvation. Solvation is the solvent surrounds the solute. They're attracted to each other and it pulls it apart. Okay? Guys are doing great. So here it is, polar solute in a polar solvent. Notice that the pink dots are the crystal, the blue blobs are water, the water surrounds the pink dots, pulls it apart. Okay, that's solvation. That's polar and polar. These are ionic, meaning they have a charge. They have positives, they have negatives. Water is a polar substance. It has a positive side and a negative side. The positive side grabs the negative. The negative grabs the positive. Opposites attract, right? Now here's what happens if I take a polar solute in a nonpolar solvent. So if I take ionic compound and put it in like oil, there's no charges. They surround it, but they don't break it apart. They don't mix. They're immiscible, right? They're not soluble. They're insolvent. All right, so polar breaks down polar, nonpolar breaks down nonpolar. Charge breaks down charged, non-charge breaks down non-charged. Now here's an example of non and non. Okay, here I have a nonpolar, there's no charge, that's the green squiggles, and a nonpolar solvent, that's the blue dots. Because neither of them have charges, they're attracted to each other. There's weak IMFs, intermolecular forces, that pull them apart. Okay, so it's still solvation, it's just nonpolar. Now again, if I have nonpolar solute and I mix it with a polar solvent, like water, water's charged. They're not going to dissolve. It's immiscible. It's insoluble. It will not break it apart. Okay. So what factors can influence the solubility of a substance? Okay. Number one, agitate, stir it. You guys ever make Kool-Aid, right? You dump in the powder, you dump in the sugar, you're done, right? No, it doesn't work because all that stuff will sit on the bottom. But you stir it up and it dissolves. Now, actually, you could put the sugar in the Kool-Aid and leave it, and it'll mix, but it'll take a long time. You stir it, you shake it. All of a sudden, that solubility, that ability to dissolve, solubility, ability to dissolve, it increases. It goes faster. Okay, so that's one thing. You can heat it. When things get warmer, think about those molecules. They go faster and faster, right? They go really fast. And that increased speed increases the speed at which it dissolves, solubility. So that's another thing you can do. And then the last thing is you can break it into pieces. Okay, so when I was a kid, now I'm old, when I was a kid, we didn't have much money, but my parents tried to do their best with what we had. So they wanted to give us everything they could, including good food. So they wanted to give us orange juice, good with vitamin C, but they couldn't afford like the Tropicana orange juice. So we got concentrate cans. I don't know if you've ever seen the orange juice concentrate. It comes in a little can and you peel the top and it's like a frozen clump of freezy, but it's like straight concentrate oranges. It's sour and nasty, but whatever. So every morning we'd open it up, pop it out, throw it in the pitcher, and then we'd fill it with water. Okay. And we could stir it and take forever. But if you took your little stirring rod and you broke it into little pieces and stirred it and chunked it and broke it apart and broke that big clump down into little clumps, it dissolved a lot faster. Why is that? Because the two pictures on the screen, the big crystals, there's actually less surface area for the water to surround and break it apart. Whereas if you make it smaller, there's more surface area and the water can pull it apart better. Okay, so there's three things you can do to increase solubility. You can stir it or shake it, you can heat it up, or you can break it into little pieces. Okay, pressure. That's the last thing. You can increase pressure. Okay, why does that work? Because pressure, again, as you increase pressure, right, those molecules are moving faster. Any movement of molecules moving faster will cause solution increase. So what's the conclusion? Solubility, the ability to dissolve, solubility, the ability to dissolve goes up when molecules move faster, when there's more collisions happen. And that happens by shaking, that happens by heating, that happens by adding pressure, right? And that happens by breaking it up into smaller pieces. Guys, that's a lot. Woo! Okay, but we're done. That's all we got. Oh, what happened? Okay, so I lost you. That's fine. So make sure you guys go on. Get onto Google Classroom, right? That's not the form you need. I always stink with the technology stuff. Whatever. Is that it? That's a different thing. Whatever. You can see my face. So get onto Google Classroom. Make sure you turn in the notes you just took. If you didn't take the notes, go back to Google Classroom. I posted that PowerPoint. You don't have to listen to me yap. But fill in the notes, turn it in. Don't forget about the V.O.D, which you just are watching right now, the God, gratitude of the day, and the quad, the question of the day, and then you're done. Boom, way to go. Keep going, guys. You're doing great. Week's almost done. Miss you. Can't wait to see you. You guys rock. Later.